All right, this video just is going to go over the first half of the PowerPoint, so if you print those off, just kind of be aware I'm covering just the first part. So we're going to talk about periodic trends and kind of the how and why they occur. So there's a little bit of a history. I'll show you guys a video about this. And there was a scientist called Dmitry Mendeleev, and he taught chemistry in terms of properties and was determined to make a table regarding this. So in the mid-1800s, 1800s are really kind of the century of chemistry. He figured out molar masses of elements, well, didn't figure them out. Since the molar masses were known, he wanted to make sense of all of these elements and put them in some sort of order. So he wrote down those elements in order of increasing mass and found that there was a pattern of repeating properties with them. So what he did is he then started putting them in rows based on those repeating properties. And he developed the first periodic table that is close to what we use today. There had been other periodic tables assembled, but his made a lot of sense, and we still use a variation of it today. So he put these elements according to the repeating properties in groups which went down. And these groups had similar properties, and as you went down the group, the elements increased in atomic mass. And he found some inconsistencies, though. The problem was he felt like there were properties that were more important than by mass. So he ended up switching the order, and he ended up grouping them by atomic number instead. There were some gaps. He actually predicted that there were elements that occurred, and he predicted their properties before we even knew what they were. And then when those elements happened to be discovered, he was right. He found that there were holes. There should have been certain elements in certain spots, and he thought they just must not be discovered. But based on the elements around them, that these must be their properties. He predicted more about these unknown elements than the people that discovered them. He actually ended up correcting some of these people. So that was pretty significant. You can determine a lot about an element based on their place on the periodic table that Mendeleev developed. So the modern periodic table, they still are grouped by elements. Similar properties are in the same column. And they are in order of increasing atomic number. The increasing atomic number and their mass tend to agree when you're high up on the periodic table, but as you go lower on the periodic table, you'll notice that it does go by their atomic number, so the number of protons they have, and not always by mass. You'll see a couple are flip-flopped as you go down further in the periodic table. There was a column added that Mendeleev never even knew about, and that's the noble gases. You can't see them, they don't react, so how would a guy in the mid-1800s even know that they existed? He didn't. So we added that column. And here's what it looks like today. His was similar. We group it based on the concepts that he developed, but this is our periodic table. And I've color-coded it on the screen so that you see the periods, not the groups, but the periods are all different colors. This is period 1 in green, period 2 in purple, period 3 in pink, and so on. Okay, so these horizontal rows are called periods, and there are 7 of them. These get inserted up into the periodic table up above. The vertical columns are called groups, and they also can be called families, and they are placed into these columns or groups by similar properties. So these are the ones we pay the most attention to. These guys in the middle are the transition metals, and they're somewhat irregular. They are very significant, but they don't have names for each group besides just these are the transition elements. So the D and the F blocks, they kind of get lumped together. But group 1A, like you'll see this either called group 1, 2, 3, 4, 5, 6, 7, and 8, or 1A, 1B, 1A, 2A, 3A, and that sort of thing. They're the main group elements, and they all have names. The ones that we focus on the most, though, are, in terms of names, are 1, 2, 7, and 8. Okay, but like I mentioned a minute ago, group B elements, they're the transition elements. These guys right here, I said, belong over here, and they're the inner metals. So group 1A, like I said, these are the main group elements. We pay most attention to them. Group 1A, though, are the alkali metals. They're very reactive. And group 2A are the alkaline earth metals. They're still reactive, but not quite as much. They're less reactive, but still never really found alone in nature. For instance, You know, sodium, potassium over here as the, I should go back, in the group 1A, they're so, you never find them by themselves. They're reactive with water, which is one of the most abundant things on Earth. So you're not going to see it in its pure form very easily if it reacts with water. Okay, so these guys all right here, the alkali metals, they react with water. The alkaline, like I said, still less reactive, but pretty reactive, so you don't find them in nature either. And then group 7A over here, these are called the halogens, which you should know already. They're pretty reactive as well. And group 8 are significant because they have a complete what's called valence shell, which we'll get into in a few minutes. And they are the noble gases. They don't want to react because they're happy. They have a full valence electron shell. Okay, so these groups right here are called the main group elements. The main group elements are the S and P blocks. If you look, here's the S block and here's the P block. So their valence shell electrons are, like, these guys have one valence electron. This group all have two. And then we kind of ignore the transition and inner metals. And these have 3, 4, 5, 6, 7, and 8 is kind of how we treat them. We simplify the periodic table, especially in this class. So they're the main group elements that are just the S and the P blocks. The valence shell electrons can be lost, gained, or shared. So that kind of determines their reactivity. You know, pretty much with the exception of nuclear chemistry for everything else has to do with electrons. So when all of the S and P orbitals are filled, the element becomes much more stable, is in a more low energy configuration, or if you want to personify the atom, which isn't necessarily, you know, accurate, but it's easier to understand, these elements become happy. They have an octet, basically meaning they have 8 electrons, they have full S and P orbitals, so they're much more stable or happy or content, if you want to think about it that way, and so they're less reactive once they achieve their octet, or their 8 valence electrons. The valence electrons are the outermost electrons, the ones in the outermost energy levels. Okay, so we'll talk about that a little more, and that has to do with electron configurations, the outermost or the highest energy levels that the electrons are filling. So if you look at the valence electrons, let's look at the alkali metals. Hydrogen has an S1, lithium, valence also is a S1. These are the inner shells. Sodium, third energy level, but still its valence electrons just in the S1 orbital, has S1 valence electron configuration. Same with the potassium, the rubidium, they're all that way. All of them are S1, all the way to the end. So S1, 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 S1. Okay, all 7 of them. The lining up of this is a little off. I just noticed, my apologies. But if you look, 1, 2, 3, 4, 5, 6, 7, these 7 elements all have an S1 valence electron. And that's it. That's what's in their valence shell. These are all inner electrons in their inner energy levels. They aren't available to react. They're tucked away, hidden a little more. Okay, so because they all have one valence electron in their outermost shell, that's what determines their reactivity. They have similar reactivities, so they're in the same group. If you look at the valence shell for the noble gases, helium's a little bit of an exception. It's just S2, but the first energy level only has 2 electrons in it. So you kind of say it has an octet because it acts like it has an octet. It acts like it has full valence shell, full energy levels, because the first energy level only has 2 electrons. So it sort of has a fake octet of 2 electrons. So it's full, so it's happy, it's content, it's unreactive with S2. Neon is S2P6. You add up the 2 and the 6, that equals 8, has an octet, it's unreactive. Argon, despite what's all on its inner shell right here, it's S2P6. It has an octet, it's unreactive. Krypton, same thing. Don't mind that. That's a little bit of an error right there. I'll change the formatting after this. Just noticed it. My apologies, but that 3 should be green. There's nothing significant about the 3. And same thing for the xenon. S2P6, S2P6 for the radon as well. Okay, so that helps explain the groupings here. They're all S2P6. They all have full shells. They're unreactive, so they behave similarly, which is why they're all in the same group. Okay, first trend we're going to look at is atomic size. First problem is, where do you start measuring an atomic size? You got all this electron cloud, so it's kind of hard to figure out like exactly how big is the atom if there's just this cloud of swarming electrons all over the place. So the electron cloud, because it doesn't have an edge, we're going to go by measuring more than one atom at a time, and we look at what's the distance from one nucleus to another. If they're bonded together, this is the radius of one of them, so half the distance between the two nuclei is the radius of one atom. So that's how we figure out an atomic size. Now, there are trends in atomic size across the periodic table, and those trends are influenced by two factors. One, how many energy levels does the atom have? And the higher the energy level, the further electrons are away, so the bigger the atom's going to be. And the other is the charge of the nucleus. The stronger or the bigger the charge of the nucleus, the more pull it's got on the electrons, and it's going to keep those electrons closer to the nucleus, and therefore it's going to be a smaller atom. So if you look in a group, hydrogen only has one energy level, so it's small. Lithium has electrons in the second energy level, so it's bigger. Third energy level, fourth energy level, fifth energy level, as you can see, they're getting bigger. So as you go down a group, each atom has another energy level, therefore the atoms get bigger. That's hopefully pretty easy to understand. With periodic trends, slightly more complicated. As you go across, and you look here, as you go across a period, the radius gets smaller. Why? Because you're still in the same energy level. But what happens in this energy level, like for sodium, we're in the third energy level. Magnesium's also in the third energy level, and aluminum and silicon and phosphorus, etc. Okay, so still in the third energy level, but what happens is you are adding protons. So the nucleus is getting stronger, but the electrons are still the same distance away from that nucleus. As the nucleus gets stronger and stronger and stronger and stronger, the nucleus has a stronger pull on the electrons, and they therefore, in that third energy level, get closer and closer to the strong pull of the nucleus. Sodium has, and pardon me, I keep glancing back at the periodic table, sodium has 11 protons, and it's in and those outer electrons are in the third energy level. Magnesium has 12 protons, but those electrons in the outermost area are still in the third energy level. So there's 12 protons pulling on the electrons here, 13 protons pulling the electrons here, 14, 15, 16, 17, 18 electrons in argon, 18 protons, excuse me. So 18 protons for argon are pulling on the electrons in the third energy level for argon, versus only 11 protons pulling on the electrons in the third energy level for sodium. So stronger nuclear charge causes them, as you go across a period, to gradually get smaller. So same energy level, but more nuclear charge, just kind of a summary. All right, so the outermost electrons are closer as you go across. And you can see here, here's the atomic radii. They get bigger in general, they get bigger as you go down and smaller as you go across. Okay, so that is the first trend. And you can see the trend here. It jumps up as you go up to a higher energy level. It jumps up, and then as you add nuclear charge or add protons, they gradually get smaller. Same here, a little bit of a blip. We'll go over stuff like this in later on in the chapter, and also if you go into a higher level chem course, these little blips here are explained. Okay, but the overall trend. Ionization energy is something that we're going to talk about in the next video. We're going to go through the rest of the trends, but I wanted you to understand the periodic table and how some of these trends occur. So that is it for now.